Somewhere in the darkness between the stars, a planet is moving alone. No sunrise touches its mountains. No sunset colors its sky. No parent star holds it in a warm and familiar orbit. It does not belong to a solar system in the way Earth belongs to the Sun. It has no year measured by a journey around a star. It drifts through the galaxy itself, carried by gravity, memory, and motion, like a silent island crossing an ocean of night. These worlds are called rogue planets. They are also known as free-floating planets, orphan planets, or wandering planets. They are planets beyond our solar system that are not gravitationally bound to a star. Some may have been born around stars and then thrown away. Others may have formed almost like tiny stars, collapsing directly from clouds of gas and dust, but never growing large enough to ignite nuclear fusion. NASA describes rogue planets as free-floating exoplanets, untethered to any star. They are among the loneliest objects in astronomy. But loneliness in the universe does not always mean emptiness. A rogue planet may still have an atmosphere, it may still have clouds, it may still have storms, it may still have moons. Deep beneath ice, it may even have hidden oceans, warmed by internal heat. Some may be frozen stone. Some may be dark gas giants. Some may glow faintly in infrared light, still warm from their formation. Some may be as small as Mars. Some may be many times the mass of Jupiter. Some may be so strange that scientists still debate whether they should be called planets at all. The mystery is not only that they exist, the mystery is how many there are. Because rogue planets are difficult to see, the galaxy may be filled with them without us noticing. They do not shine like stars. Many are too cold and faint to detect directly. They can pass through the Milky Way for billions of years, almost invisible, known only when their gravity briefly bends the light of a more distant star. NASA-supported research has suggested that rogue planets may far outnumber planets that orbit stars, with one estimate proposing that the Milky Way could contain around 20 times more rogue planets than stars, though this remains an active area of study. If that is true, then our galaxy is not only a galaxy of stars, it is a galaxy of lost worlds. And tonight, we will drift with them, through the dark spaces between suns, through the chaos of young planetary systems, through the quiet aftermath of ejection. Through star-forming clouds, gravitational encounters, microlensing flashes, frozen atmospheres, hidden oceans, and the possibility of life without daylight. This is the story of rogue planets, the planets that travel without a star. A rogue planet is a world without a sun. That is the simplest definition. But in astronomy, simple definitions often hide complicated questions. A planet in our own solar system is easy to imagine. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all orbit the Sun. Their paths may be different, their surfaces wildly unlike one another, but they share the same central star. They are members of a system. A rogue planet is different. It is not bound to a star. It travels through interstellar space, pulled not by one nearby sun, but by the gravity of the galaxy as a whole. It may pass near stars, clusters, nebulae, or other planets, but it does not settle into the kind of stable orbit that defines familiar solar systems. It is a world separated from home, or perhaps a world that never had one. The word rogue can make these planets sound dangerous, like cosmic intruders wandering toward us from the dark. But most rogue planets are not threats. They are not racing through space with the purpose of destruction. They are simply following gravitational paths, just as stars do, just as the Sun itself orbits the center of the Milky Way. The galaxy is vast. Even if rogue planets are common, space is so empty that close encounters are rare. Still, the idea is haunting. A planet without a star changes the emotional meaning of a planet. We usually think of a planet as a place with a sky, seasons, light, and a source of warmth. Even the cold outer planets of our solar system receive some sunlight. Even Pluto, distant and dim, sees the sun as a bright star. But a rogue planet may see no sun at all. If it has a surface, the sky above it may be almost completely black. The stars would shine, but they would not warm the ground. A nearby galaxy might appear as a faint milky glow. The Milky Way might stretch overhead like a frozen river of light. But there would be no day, only night. And yet, a rogue planet is not necessarily dead. Planets have internal heat. Some heat remains from formation, when gravity compressed material and collisions built the planet. Some heat comes from radioactive decay inside rocky worlds. Some may come from tides if the planet has moons, or if it once had a close gravitational relationship with another object. Gas giants can retain heat for long periods, slowly radiating it away into space. A planet does not need a star to exist. It only needs mass, gravity, and history. This is part of what makes rogue planets so fascinating. They blur the line between planet and star, between solar system and interstellar space, between object and environment. If a world forms like a star but has the mass of a planet, is it a planet? If a planet forms around a star but is later ejected, does it remain a planet? If two Jupiter-mass objects drift together as a pair, are they binary planets, failed stars, or something else? Astronomy is still working through these questions. The term rogue planet is useful, but it is not always precise. Scientists may also use terms like free-floating planetary mass object, isolated planetary mass object, substellar object, or orphan planet. These names reflect uncertainty about mass, formation, and classification. The universe does not always sort itself into human categories. Rogue planets exist in the gaps. They are planets without suns, but also clues without simple labels. To imagine a rogue planet, begin with darkness. Not the darkness of a room when a lamp is switched off, not the darkness of midnight on Earth where the moon may shine and cities may glow and the sun waits below the horizon. A rogue planet's darkness is deeper. If it is far from any star, there may be no true daytime anywhere on its surface. If it rotates, it may have a cycle of stars moving across the sky, but not a day-night cycle in the ordinary sense. Rotation would still give rhythm. Winds might still circle the planet. Storms might still evolve, but sunlight would not divide the world into morning and evening. There would be no seasons caused by orbiting a star. There would be no habitable zone in the traditional sense. The temperature of such a world would depend on its atmosphere, its internal heat, its age, its composition, and its history. A young rogue gas giant might still glow warmly in infrared light. It would be dark to human eyes, but to an infrared telescope it could shine like an ember cooling after formation. Over time, it would fade. Its clouds would cool. Its atmosphere would settle into strange chemistry. Methane, ammonia, water, hydrogen, helium, and other gases might shape its weather depending on temperature and mass. A rocky rogue planet would likely be much colder unless it had a thick atmosphere capable of trapping internal heat. Without sunlight, exposed oceans would freeze. Atmospheres might collapse onto the surface as frost if temperatures fell low enough. Carbon dioxide, nitrogen, methane, even oxygen could freeze under extreme conditions. But beneath ice, the story may change. On Earth, the deep ocean does not depend entirely on sunlight. Near hydrothermal vents, life survives using chemical energy from the planet's interior. On moons like Europa and Enceladus, scientists consider the possibility of subsurface oceans hidden beneath ice shelves, warmed by tidal heating and internal processes. A rogue planet with enough internal heat and insulation could, in theory, preserve liquid water below a frozen surface. This is speculative, but it is not impossible. A rogue planet with a thick hydrogen atmosphere could trap heat efficiently. Hydrogen, though simple, can help retain warmth under certain conditions through pressure and greenhouse effects. Some theoretical studies have suggested that free-floating planets might maintain surface or subsurface conditions where liquid water could exist, though whether such worlds are common, stable, or habitable remains unknown. This possibility changes the mood of the darkness. A rogue planet may not be a dead stone. It may be a covered ocean, a hidden world, a place where the surface is silent ice, but beneath it, heat still moves. Imagine standing above such an ocean. There is no sun. The sky is black. The stars do not twinkle much if the atmosphere is thin or calm. The ground beneath your feet is ice harder than rock. Far below, perhaps many kilometers down, water shifts slowly in the dark. Minerals dissolve from rock. Heat rises from the interior. Chemistry continues. Life, if it existed there, would not know sunlight. It would not know dawn. It would not know the color of a star. It would belong completely to the planet, not to the sky. That is one of the deepest questions rogue planets ask. Can a world be alive without a sun? A planet can become rogue by being thrown away. Planetary systems are not always calm. They may look orderly after billions of years, but their youth can be violent. When stars are young, they are often surrounded by disks of gas and dust. Inside these disks, planets form. Small grains stick together. Pebbles become rocks. Rocks become planetesimals. Planetesimals collide and grow into protoplanets. Gas giants may gather thick envelopes before the gas disk disappears. But the early architecture of a planetary system can be unstable. Planets pull on one another. Giant planets migrate inward or outward through the disk. Resonances develop. Orbits cross. Worlds scatter. A close encounter between two planets can change both paths dramatically. One planet may be pushed inward. Another may be thrown outward. If the outward kick is strong enough, the planet can escape the star completely. It becomes a rogue. NASA's Rogue Planets 101 material describes ejection from planetary systems as one common formation pathway, while also noting that some rogue planets may form alone in a manner more similar to stars. The process is not unusual in gravity. When several massive bodies interact, energy and momentum are exchanged. One object can gain speed at the expense of another. In a young system with multiple giant planets, these encounters can be powerful. A planet does not need to be destroyed to lose its star. It only needs to be accelerated beyond escape velocity. The home star grows smaller behind it. The orbit opens. The planet crosses the outer regions of the system. Perhaps it passes through a distant belt of icy bodies, disturbing comets as it leaves. Then the star is no longer its anchor. The planet enters interstellar space. This may have happened many times in the Milky Way. Our own solar system may have had a more crowded past. Some models suggest that additional planets or planetary embryos could have existed early on and later been ejected or absorbed. We do not know exactly what was lost. The solar system we see today is the survivor of a long history of collisions, migrations, and gravitational adjustments. A rogue planet is one possible fossil of such chaos. It is not only a lonely world. It is evidence that planetary systems can rearrange themselves violently. Ejection may also happen in star clusters. Many stars are born in groups. In crowded stellar nurseries, young systems can pass near one another. A neighboring star can disturb a planetary system, especially its outer planets. The weaker the star's grip on a planet, the easier it is for a passing star to strip that planet away. Wide-orbit planets are especially vulnerable. A planet orbiting far from its star moves slowly and is weakly bound. A close stellar encounter can loosen or remove it. In dense clusters, such events may be more common than in quiet regions of the galaxy. Then, there are binary stars. Many stars are born in pairs or multiple systems. Planets in such systems may follow complex orbits. Some orbit one star, some orbit both. Others form in unstable regions and do not last. Gravitational interactions among stars and planets can eject worlds into interstellar space. A rogue planet, then, may be in exile. It may have formed in light within a disk near a star among siblings. Then, through no intention, no catastrophe of fire, no explosion required, it was gravitationally dismissed. Not destroyed, only released. Not every rogue planet must have been ejected. Some may have formed alone. This possibility makes the definition of a rogue planet more complicated. Stars form when cold clouds of gas and dust collapse under their own gravity. If the collapsing mass is large enough, the center becomes hot and dense until hydrogen fusion begins. A star is born. If the mass is too small for sustained hydrogen fusion, the result may be a brown dwarf. Brown dwarfs are sometimes called failed stars. Though the phrase is imperfect, they are real objects with their own physics. Some can burn deuterium for a time if they are massive enough, but they do not become ordinary stars. Below brown dwarfs are planetary mass objects. If a small fragment of a molecular cloud collapses directly, forming an object with only a few times Jupiter's mass, is that object a planet? It did not form in a disk around a star. It was never part of a solar system. But it may have a planetary mass, planetary atmosphere, and planetary temperature. Some astronomers may call it a free-floating planetary mass object rather than a planet. The difference is not just vocabulary. It touches on the question of whether planets should be defined by mass, by formation, or by orbit. If a world has the mass of Jupiter but forms like a star, is it a planet or a tiny failed star? Nature does not care about the boundary, but science needs language. Observations from star-forming regions show that very low-mass objects exist. Young, warm, free-floating bodies can be detected in infrared light because they still radiate heat from formation. ESA has reported that Euclid's infrared view of Messier 78 revealed newly formed stars and planets with instruments sensitive enough to detect objects just a few times the mass of Jupiter in that star-forming region. The James Webb Space Telescope has also pushed into this strange territory. A JWST near-infrared survey of the Orion Nebula and Trapezium cluster reported hundreds of planetary mass candidates, including objects with masses estimated below Jupiter's mass, and found that some appeared in wide binary pairs. Those results are scientifically intriguing, but they also challenge formation theories and remain part of ongoing research. These discoveries suggest that the boundary between planets and stars may be more like a mist than a wall. A rogue planet may be an ejected world. Or it may be a star that never became a star. It may be born alone in a cloud. It may be born in a disk and later cast out. It may be part of a pair. It may have moons. It may have a ring system. It may have weather. It may have a magnetic field. It may be cold and invisible or young and glowing. The variety may be enormous. And because we have only begun to detect them, our picture is incomplete. The rogue planets we can see today are probably not representative of all rogue planets. Young, massive, warm objects are easier to detect directly. Lower mass, older, colder rogue planets are much harder. Microlensing can reveal some of them, but only during rare alignments. This means our current sample is biased toward what our instruments can find. The galaxy may contain a hidden population of smaller, older, darker worlds. Worlds that formed billions of years ago. Worlds that have cooled into silence. Worlds that are there, but almost impossible to see. Rogue planets are difficult to find because they are dark. A star announces itself. It shines across light years. A planet around a star can be found by the shadow it casts when it transits, or by the wobble it causes in its star, or by reflected light, or by direct imaging if it is far enough from the glare. A rogue planet has no star to transit, no parent star to wobble, no sunlight to reflect. If it is old and cold, it may emit very little infrared radiation. It may drift through space without any obvious signal. This is why astronomers need indirect methods. The most powerful method for finding many rogue planets is gravitational microlensing. Microlensing happens when a foreground object passes almost exactly in front of a more distant background star from our point of view. The foreground object's gravity bends space-time slightly. Light from the background star follows the curved path. For a brief time, the background star appears brighter. The foreground object acts like a natural lens. If that lens is a rogue planet, the brightening may last only hours or days. NASA explains that a rogue planet's microlensing signal can last from a few hours to a couple of days and then vanish forever, making such events difficult to observe from Earth. This is a strange way to discover a world. You do not see the planet itself. You see a star briefly brighten because an unseen planet passed through the right line of sight. The event may never repeat. The planet continues on. The background star returns to normal. For a moment, the dark world left a gravitational fingerprint. Then it was gone. Microlensing is powerful because it can detect objects that emit little or no light. It is sensitive to mass, not brightness. A planet that would otherwise remain invisible can reveal itself through gravity. But microlensing requires patience, wide surveys, and luck. Astronomers must monitor millions of stars, often toward dense regions like the galactic bulge, where background stars are numerous. They look for brief changes in brightness. They separate true microlensing events from variable stars, flares, instrumental effects, and other noise. Then they model the shape of the light curve to infer what kind of object caused the lensing. A short event may suggest a low-mass, free-floating planet. A longer event may suggest a star, brown dwarf, or planet bound to a host star. But interpretations can be difficult. Sometimes a planet may be widely separated from its star rather than truly free-floating. Sometimes the host star is too faint or too far away to detect. Astronomers must be careful not to claim more certainty than the data allow. This is part of why rogue planets remain mysterious. They reveal themselves as brief mathematical shadows in starlight. They are not photographed like familiar planets. They are inferred. We know them by the temporary distortion they create. Future telescopes are expected to change this field dramatically. NASA's Nancy Grace Roman Space Telescope is designed to conduct a space-based microlensing survey. NASA has reported that Roman could find hundreds of Earth-mass rogue worlds and study free-floating bodies across a wide mass range. Roman will not make rogue planets easy, but it may turn them from rare hints into a population. And once we have a population, we can ask bigger questions. How many rogue planets are there? What masses are most common? Are Earth-mass rogues abundant? Do giant rogues dominate? How many were ejected? How many formed alone? Do planetary systems commonly lose worlds? Are rogue planets a normal byproduct of planet formation? A galaxy of hidden worlds may soon become a galaxy we can begin to count. Imagine a young planet newly ejected from its star. At first, it may not seem completely dark. If it is a gas giant, it may still radiate internal heat. Its atmosphere may glow faintly in infrared. Deep storms may churn. Heat from formation may rise through clouds. Lightning may flash in enormous belts of gas. If it has rings, those rings may no longer shine with sunlight, but they may still exist as dark arcs of ice and dust. If it has moons, they follow, or some follow. The ejection that frees a planet from its star may also disturb its moon system. Close encounters with other planets or stars could strip moons away, but a massive planet with close moons might keep them. Those moons would then become rogue moons, orbiting a rogue planet through interstellar space. This is one of the most haunting possibilities in astronomy. A moon traveling with a planet that has no star, a world around a world both in darkness. Tidal forces may heat such moons if their orbits are eccentric. This is what happens in our solar system with Io, which is heated by gravitational interactions with Jupiter and other moons. Europa and Enceladus may preserve subsurface oceans, partly because internal and tidal processes keep them warm. A rogue gas giant with moons could, in theory, carry small ocean worlds through the galaxy. No sunlight, but perhaps heat. No seasons, but perhaps tides. No day, but perhaps chemistry. A rocky rogue planet's first night would be different. As it leaves its star, sunlight fades. The planet's surface cools. Oceans begin to freeze from the top downward. Weather changes. Clouds collapse or transform. The atmosphere may shrink, condense, or partly freeze depending on composition and pressure. If the planet has a thick hydrogen atmosphere, it may retain more heat. If it has a thin atmosphere like Mars, the cold may dominate quickly. The surface becomes hostile. But beneath the surface, thermal inertia matters. Rock and water store heat. Ice insulates. Radioactive elements release energy slowly. A thick ice shell may protect a subsurface ocean for long timescales if the planet begins with enough water and internal heat. Such a world would be sealed off, but not necessarily frozen solid. The transition from star-bound planet to rogue planet could take time. The star becomes a memory. At first, it is still a bright point in the sky. Then, after thousands or millions of years, perhaps it is only one star among many. Eventually, the planet's original system may be impossible to identify. The rogue world becomes galactic rather than solar. It no longer belongs to the architecture of one star. It belongs to the Milky Way. Weather does not require sunlight, though sunlight is the main driver of weather on Earth. On a rogue planet, weather would depend on heat from within, atmospheric composition, rotation, chemistry, and pressure. A young gas giant could have powerful internal heat. Hot material rising from deep layers could drive convection. Clouds could form at different levels, made not of water alone, but of ammonia, methane, sulfides, salts, or other compounds depending on temperature. Jupiter and Saturn already show that gas giants have internal heat and complex weather. Jupiter emits more energy than it receives from the Sun. Saturn does too. Their atmospheres are shaped by sunlight, but they are not powered by sunlight alone. A rogue gas giant would be colder and darker, but not necessarily calm. Its storms might be hidden in infrared, bands could form, vortices could last for centuries. Lightning could illuminate cloud decks from within, brief flashes in a sky without dawn. If the planet has a magnetic field, auroras may flicker near its poles, driven by charged particles from the interstellar medium or from moons and magnetospheric processes. A rogue planet may be dark to us, but not entirely dark to itself. Imagine a black sky above a hydrogen-rich world. There is no sun, but the atmosphere glows faintly in infrared. Clouds move in slow belts. Deep below, heat rises from the planet's formation. Far above, charged particles spiral along magnetic field lines. Pale auroras shimmer over polar darkness. On a rocky rogue planet, weather may be stranger. If the atmosphere remains gaseous, winds might be driven by heat escaping from the interior. But if the world is very cold, many gases could freeze. Carbon dioxide might fall as snow. Nitrogen could form frost or liquid under the right conditions. Methane might behave as a volatile fluid, like on Saturn's moon, Titan, though without sunlight, the chemistry would differ. If the atmosphere collapses almost completely, the surface may become silent. No wind, no clouds, no rain. Only ice, rock, and stars. But even a nearly airless rogue planet may experience geological change. Impacts can occur. Internal heat can drive volcanism for a time. Cryovolcanism may happen on icy bodies if subsurface liquids exist. Tectonic stresses can crack ice. Geysers may erupt from hidden reservoirs. Without sunlight, change slows, but it does not necessarily stop. Time on a rogue planet may be measured not by days and seasons, but by cooling, freezing, cracking, and drifting. Its climate is not tied to a year. Its weather is a memory of formation. The question of life on a rogue planet is speculative, but it is scientifically meaningful. Life as we know it needs liquid water, chemistry, energy, and time. Sunlight is useful, but it is not the only possible energy source. On Earth, ecosystems exist in deep oceans, caves, and hydrothermal vent systems where sunlight is absent. They depend on chemical energy. This does not prove that rogue planets can host life. But it means sunlight is not the only path. A rogue planet with a subsurface ocean could, in principle, provide liquid water. If the ocean is in contact with rock, chemical reactions may provide energy. If internal heat lasts long enough, stable environments could persist for long periods. If the planet has a thick ice shell, the ocean may be protected from radiation and impacts. Such a world would not look alive from outside. It would look frozen. The life, if it existed, would be hidden. It might be microbial. It might live near mineral vents. It might use chemical gradients rather than photosynthesis. It might never evolve eyes because there would be no sunlight to see. It might never know a surface because the surface would be deadly cold. It might never experience a sky. This possibility expands the idea of habitability. The traditional habitable zone is the region around a star where a planet could have liquid water on its surface. But rogue planets do not orbit stars, so the traditional habitable zone does not apply. Instead, scientists consider other kinds of habitability: subsurface oceans, thick insulating atmospheres, internal heating, tidal heating, and chemical energy. These are harder to detect. If we found a rogue planet with life beneath ice, how would we know? It might not produce atmospheric biosignatures. It might not alter visible light. It might be impossible to study directly unless it passed extremely close to the solar system, which is unlikely. For now, the idea remains theoretical. But it matters because it asks whether life is tied to starlight or to planets themselves. Earth's biosphere is strongly shaped by the sun. Photosynthesis transformed our atmosphere. Seasons influence ecosystems. The day-night cycle shapes biology, but the deep biosphere reminds us that life can exist in darkness. A rogue planet, if habitable, would be the ultimate dark biosphere, a world where life survives not because a star shines, but because a planet remembers heat. A rogue planet does not wander randomly. It follows the gravity of the galaxy. The Milky Way is a vast rotating system of stars, gas, dust, dark matter, clusters, and planets. The Sun orbits the galactic center at a distance of about 26,000 light-years. Rogue planets also orbit within the galaxy, moving through its gravitational field. Their paths may be shaped by their birthplaces, ejection speeds, encounters with stars, and the galaxy's mass distribution. A rogue planet ejected from a young system does not simply fly straight forever. It becomes another object in galactic orbit. It may pass through spiral arms, star-forming regions, dark molecular clouds, and quiet interstellar space. It may cross regions rich with stars, then drift into sparse areas. It may travel for billions of years without a close encounter. Space is large enough that even a galaxy full of rogue planets can still be mostly empty. If you stood on one, the stars would slowly change over enormous timescales. Constellations would not be permanent. Nearby stars would pass and fade. The galactic disk would stretch overhead. The planet might move through interstellar gas and dust, but these particles are so thinly spread that they would not feel like wind in the ordinary sense. There is no air in interstellar space. But there is still environment. Cosmic rays strike. Interstellar dust impacts. Magnetic fields thread the galaxy. The planet's own magnetic field, if it has one, may shield some charged particles. Its atmosphere, if thick enough, may absorb radiation. Its surface may be weathered by micrometeorites and high-energy particles. Over billions of years, the planet cools. If it is rocky, internal radioactivity declines. If it is a gas giant, heat leaks away. If it is icy, the ice thickens. If it has an ocean, the ocean may slowly freeze unless enough heat remains. If it has moons, their orbits may evolve. A rogue planet is not static. It is a slow story, a story told in darkness. Rogue planets sometimes appear in popular imagination as threats. A hidden world enters the solar system. It disturbs orbits. It brings disaster. It collides with Earth. It arrives from darkness with no warning. Science does not support these fear-based stories. Rogue planets may be common, but the solar system is very small compared with the distances between stars. A rogue planet passing close enough to seriously disturb Earth would be extraordinarily unlikely. Astronomers survey the sky for near-Earth objects and large bodies in the solar system. A massive planet entering the inner solar system would not remain hidden until the last moment. Its gravity and reflected or emitted radiation would give it away. The real science of rogue planets is not a doomsday story. It is a formation story. Rogue planets teach us about how planetary systems form, evolve, and sometimes eject worlds. NASA's educational material emphasizes that studying rogue planets helps scientists better understand how planetary systems form and change over time. They are not interesting because they might destroy us. They are interesting because they reveal what planets can become when they are no longer protected by the architecture of a star system. They show us that planet formation may be messy. They show us that not every world stays where it was born. They show us that the galaxy may contain a shadow population of planets we are only beginning to detect. In a way, rogue planets make the universe feel larger. The stars we see are not the whole story. Between them may be countless worlds. How many rogue planets are there? This is one of the biggest questions. The answer depends on mass. There may be many Jupiter mass rogue planets. There may be even more Earth mass rogue planets. There may be Mars mass rogues, Moon mass objects, icy bodies, planetary embryos, and fragments. But the smaller and colder they are, the harder they are to detect. NASA-supported research has estimated that rogue planets could be far more numerous than stars, possibly with trillions in the Milky Way. But this estimate depends on survey interpretation and must be refined by future observations. This uncertainty is important. When we say rogue planets may outnumber stars, we are not saying we have counted them all. We are saying that observations and models suggest a large hidden population. Microlensing surveys provide clues. Formation simulations provide theoretical expectations. Young star-forming regions reveal some low-mass, free-floating objects. But the full census is incomplete. The Nancy Grace Roman Space Telescope is expected to improve this dramatically. By observing from space with a wide field of view and stable sensitivity, Roman should detect many microlensing events that ground-based surveys miss. NASA describes Roman as a game changer for rogue planet searches because microlensing events are brief and hard to catch from Earth. If Roman finds many low-mass rogue planets, that would suggest planetary ejection is common. If it finds fewer than expected, formation models may need revision. If it finds a mass distribution that peaks at certain sizes, that will tell us something about the violence and efficiency of planet formation. Counts matter because they connect rogue planets to the history of ordinary solar systems. Every rogue planet may be a clue to a system that once lost something. The Milky Way may be filled with such lost histories. A rogue gas giant may be the easiest kind of rogue planet to imagine. It would be like Jupiter but without the sun. Massive, cloud-covered, mostly hydrogen and helium, deep atmosphere, no solid surface in the familiar sense, internal heat rising from below, powerful gravity. Possibly rings and moons. A world that is more like a weather system than a landscape. If it is young, it may be warm enough for infrared telescopes to detect directly. This is why young star-forming regions are useful places to search. The planets or planetary mass objects there have not cooled completely. They still glow with leftover heat. Over time, a rogue gas giant becomes colder and dimmer. Its clouds change as temperatures drop. Compounds condense at different layers. Water clouds may form deep down. Ammonia clouds may appear. Methane chemistry may become more important. Eventually, the planet becomes a cold, dark giant, radiating faint heat into interstellar space. But even then, it is not nothing. The pressure inside is immense. Hydrogen may behave in exotic ways. Magnetic fields may be generated by conducting interior layers. Moons may orbit, rings may persist. A rogue gas giant could be a tiny system by itself. If it has moons, those moons may be more interesting than the planet for habitability. A moon with internal heating, tidal stresses, or radioactive decay could preserve subsurface liquid water. Around a star, such moons would also receive sunlight. Around a rogue planet, they would not. But tidal heating can be powerful. This creates the possibility of miniature dark solar systems, a giant planet and its moons drifting through the galaxy, forming a family without a star. The planet is the center. The moons are the worlds. The sky is eternal night. A rocky rogue planet may be closer to Earth in structure, but far more alien in environment. If Earth was somehow ejected from the solar system, the consequences would be severe. Sunlight would fade, surface temperatures would fall, oceans would freeze from the top down. The atmosphere would change. Eventually, much of the surface would become locked in ice and darkness. But Earth's interior would remain warm for a long time. Radioactive decay and residual heat would continue. The deep ocean might survive beneath ice for some period. Hydrothermal vents could continue. Life on the surface would collapse, but deep life might persist longer. This thought experiment shows how a rogue Earth-like planet might not be instantly sterile. But maintaining habitable conditions for billions of years would be difficult and would depend on many details: mass, water content, atmosphere, internal heat, ice thickness, geologic activity, and whether enough chemical energy remains available. A rocky rogue planet with a thick hydrogen atmosphere might be warmer than expected. Hydrogen is light and can escape easily from small planets, but a more massive rocky planet, or one formed in a hydrogen-rich environment, might retain a thick envelope. Such an atmosphere could act as insulation, trapping heat from the interior. This would not be Earth-like habitability. The pressure might be enormous, the atmosphere might be strange, the sky might be opaque, but liquid water might exist somewhere. A rocky rogue planet without such insulation would likely become a frozen desert. Its atmosphere could condense, its surface could crack, its oceans could become global ice. Volcanic regions might remain locally warm for a time, but without sunlight, the surface environment would be harsh. Still, the idea of rocky rogue worlds matters because it expands the range of planetary outcomes. Not every planet stays in a system. Not every Earth-sized world receives sunlight. Some may become cold archives of geological history, drifting forever. Rogue planets are dark, but they are not the same as dark matter. This distinction is important. Dark matter is the unseen mass that appears to shape galaxies, galaxy clusters, and the cosmic web through gravity. It does not seem to emit, absorb, or reflect light in the ordinary way. Most evidence suggests it is not made mainly of normal planets, stars, gas, or dust. Rogue planets are made of ordinary matter, also called baryonic matter. They are dark because they are faint, not because they are a new kind of particle. A galaxy could contain many rogue planets and still not explain all dark matter. ESA notes that substellar objects such as brown dwarfs and free-floating planets have been considered as possible dark matter candidates. But current knowledge suggests there are not enough of them to solve the Milky Way's dark matter mystery. This means rogue planets are part of the dark population of ordinary matter. They may contribute to the galaxy's unseen inventory, but they are not the main answer to dark matter. Still, they remind us that darkness has categories. Some things are dark because they are cold, some because they are distant, some because they are hidden behind dust, some because they interact weakly with light, some because they emit no light of their own. A rogue planet belongs to the first kind of darkness. It is matter we understand in principle, but struggle to see in practice. Some of the most interesting rogue planet candidates are found in young star-forming regions. These are places where gas and dust collapse into stars, brown dwarfs, and planetary mass objects. They are messy, luminous, and filled with newborn systems. Because the objects are young, they are still warm. Infrared telescopes can peer through dust and detect heat. The Orion region is especially important. It is nearby in astronomical terms and rich with young objects. Observations from Euclid and JWST have revealed low mass and substellar populations there, helping scientists study how star and planet formation extends down into the planetary mass range. Euclid's Messier 7-8 observations, for example, revealed more than 300,000 new objects in one field and demonstrated sensitivity to objects just a few times Jupiter's mass. Young, rogue planets in such regions may not have been ejected yet. Some may have formed directly. Some may be in the process of being scattered. Some may be bound to stars at very wide distances. Some may later be captured or disrupted. These regions are nurseries, not settled systems. They show us the raw material of planetary populations before time has sorted them. The discovery of planetary mass candidates in Orion is especially intriguing because some appear to be in pairs. The reported Jupiter mass binary objects, or jumbos, are difficult to explain if they are truly planetary mass pairs drifting together. Their existence challenges simple formation models, though their interpretation remains an active research topic. If such objects are real and common, they suggest that planetary mass bodies can form in ways we do not fully understand. Perhaps cloud fragmentation can produce tiny systems. Perhaps planets can be ejected in pairs. Perhaps some detections are more complex than they appear. The mystery is open. And in science, an open mystery is not a weakness. It is where discovery begins. There are two main ways to find rogue planets. One is direct imaging, the other is microlensing. Direct imaging works best for young, massive, warm rogue planets. These objects still glow in infrared light. They are easiest to find in young star clusters and star-forming regions, where their age is known and their heat has not yet faded. Infrared telescopes can detect them against the background of space. But direct imaging struggles with old, cold, low-mass rogue planets. A cold Earth-mass rogue planet drifting through the galaxy would be nearly impossible to image directly with current technology unless it were extremely close. Microlensing can detect darker worlds. It does not require the rogue planet to shine. It only requires a rare alignment with a background star. The planet's gravity bends and magnifies the star's light. Astronomers record a brief brightening event. The shape and duration of that event contain information about the lensing object. This method is sensitive to otherwise invisible planets, but it is also temporary. The event happens once. The planet moves on. You cannot usually point a telescope later and see it again. This makes rogue planet science feel almost ghostly. A world appears only as a brief change in another star's brightness. A hidden mass writes a signature in light. Then the signature fades. Future surveys may collect enough of these ghostly moments to build a statistical picture. Even if we cannot study each rogue planet in detail, we can count events, we can estimate masses, we can infer abundance, we can compare observations with simulations. The goal is not only to find individual lonely worlds, it is to understand the hidden population. A rogue planet has no year around a star, but it still has time. It may rotate. If it rotates, there is a spin period. One side turns toward the galaxy, then away. But without a nearby sun, this rotation does not create day and night in the familiar sense. There may still be tides. If the planet has moons, their gravitational pull may raise tides in oceans, ice, or atmosphere. If the moons have eccentric orbits, tidal heating may warm their interiors. The planet and its moons may exchange angular momentum. Orbits may slowly evolve. There may still be seasons of another kind, not seasons from sunlight, but epochs of cooling, a young warm phase, a fading infrared phase, a frozen surface phase, a deep interior phase, a long dark equilibrium. The planet's history becomes thermal rather than solar. It is shaped by how heat escapes. The passage of time is measured by cooling curves, atmospheric chemistry, orbital encounters, and internal evolution. This is very different from Earth. Earth's life is tied to the sun. Our calendars, agriculture, climate, and biology all depend on solar cycles. A rogue planet would have no such rhythm unless it carried one internally. If life existed beneath its ice, it might evolve around chemical cycles, geothermal pulses, tidal rhythms, or planetary rotation. It would not know spring. It would not wait for dawn. It would not look upward for energy. It would look inward. Rogue planets are scientific objects, but they also affect imagination. They feel lonely. The phrase "planet without a star" carries emotion. It suggests exile, silence, and distance. It makes us imagine a world cut off from warmth, drifting through darkness. But this loneliness is human language. The planet does not feel abandoned. It does not know it has no sun. It follows physics. Still, the image is powerful because we understand the importance of belonging. Earth belongs to the sun. The moon belongs to Earth. Our days belong to sunrise. Our years belong to orbit. A rogue planet has lost the structure that makes planets familiar to us. That is why it feels mysterious. It is not simply a world in darkness. It is a world outside the pattern. And yet, in the galaxy, rogue planets may be normal. If they are abundant, then starless worlds are not rare exceptions. They are part of the ordinary inventory of the Milky Way. Planetary systems may create them naturally. Star-forming clouds may produce them directly. The galaxy may be filled with them. Loneliness at cosmic scale may be common. A rogue planet may be isolated from stars, but not from the universe. It is still part of the galaxy, still shaped by gravity, still carrying matter forged in stars, still moving through the same cosmic web, still a piece of the universe, only darker. The cold of interstellar space is profound. Far from stars, the main background radiation is the cosmic microwave background, now only a few degrees above absolute zero. A planet in such an environment loses heat to space. Without sunlight, every exposed surface cools unless heat arrives from within. For a small rocky planet, the surface may become extremely cold. Water becomes ice. Carbon dioxide may freeze. Nitrogen may freeze under the right conditions. Chemical reactions slow, atmospheres thin or collapse. But cold is not simple. A thick atmosphere changes everything. A dense hydrogen envelope can insulate. A deep ocean under ice can remain liquid while the surface is frozen. A large planet cools more slowly than a small one. A gas giant may stay warm inside for long times. Moons may be heated by tides. The deep cold is not always total death. It is a filter. It removes surface warmth. It hides activity below. It makes life, if present, harder to detect. It makes geology slow. It makes atmosphere fragile. It turns worlds inward. The deep cold is the dominant environment of rogue planets. And yet, every rogue planet carries a small resistance to it. Its gravity holds matter together. Its interior stores heat. Its chemistry continues. The darkness outside is immense. But inside, some worlds may still glow. Can a rogue planet be captured by a star? Yes, in principle. But capture is not easy. For a free-floating planet to become bound to a star, it must lose enough energy. A simple two-body encounter usually does not allow permanent capture because the planet comes in and leaves with the same total energy relative to the star. But in more complex situations, energy can be exchanged. A rogue planet might be captured during an interaction involving another planet, a binary star, a star cluster, or a dense birth environment. The process is more likely when many bodies interact and gravitational energy can be redistributed. If captured, the planet may end up on a wide, eccentric orbit. It might become a distant outer planet. It might perturb other bodies. It might eventually be ejected again. Some very distant planetary companions around stars could, in theory, have histories involving capture, although proving such origins is difficult. The boundary between a wide-orbit planet and a rogue planet can be observationally challenging. A planet may look isolated simply because its star is too far away or too faint to detect. This is another reason scientists are careful. Not every lonely-looking planet is truly alone. Some may have stars at enormous distances. Some may be unbound. Some may be members of young associations moving together through space. Some may be borderline brown dwarfs. Classification requires data. And in the dark, data comes slowly. The next major leap in rogue planet science may come from the Nancy Grace Roman Space Telescope. Roman is designed to survey large regions of the sky with high precision. One of its major scientific tools will be microlensing. By monitoring dense star fields, especially toward the center of the Milky Way, Roman should catch many brief lensing events caused by planets and other compact objects. NASA has reported that Roman could find hundreds of Earth-mass rogue planets, and that its observations will help test theories of how these worlds form. This matters because Earth-mass rogue planets are especially hard to detect from the ground. Their microlensing events are short and faint. A space telescope can provide more continuous, stable observations, avoiding weather, daylight, and atmospheric distortion. Roman may answer questions that are currently impossible to settle. Are low-mass rogue planets common? Do they outnumber stars? Are they mainly ejected from planetary systems? Do young systems lose Earth-sized worlds frequently? Is the Milky Way filled with frozen Earths? Roman will not give us close-up images of these worlds. It will give us statistics. But statistics can change astronomy. When enough brief events are collected, a hidden population becomes visible. The unknown becomes a distribution. The distribution becomes a theory. The theory becomes a new understanding of how planetary systems live and change. The Roman era may reveal that rogue planets are not rare wanderers. They may be one of the galaxy's largest planetary populations. A rogue planet is, in many ways, a sleeping world. It is not dead exactly. It is quiet. If it has a surface, that surface may be still. If it has oceans, they may be buried. If it has weather, it may be slow and dark. If it has life, that life may be hidden from the sky. If it has moons, they may circle without sunrise. If it has rings, they may be black bands against black space. Everything about it is reduced, softened, hidden. A rogue planet is not dramatic like a supernova. It does not blaze like a quasar. It does not devour like a black hole. It does not glitter like a star cluster. It drifts. Its mystery is quiet. That is why it belongs so naturally to a sleep documentary. It is a world of slow motion, a world of darkness, a world where the loud processes of formation have ended and only the long journey remains. Imagine one particular rogue planet. It formed in a disk around a young star. There were other planets nearby, still growing, still migrating, still pulling at one another through the dusty gas. The system was unstable, orbits shifted. A giant planet moved inward, another moved outward. Smaller worlds were scattered. For a while, this planet survived. It circled the star. It saw sunlight. Maybe it had an atmosphere. Maybe it gathered ice and rock. Maybe it crossed paths with a larger neighbor. Then came the encounter. Not a collision, only gravity, a close pass. A transfer of energy. The planet's orbit stretched into a long ellipse. It moved far from the star, then returned. Another encounter changed its path again. This time the orbit did not close. The planet was leaving. At first the star was still bright, then smaller. Then one bright star among thousands, then one ordinary point in the Milky Way. The planet did not stop. It entered the galactic night. Perhaps it still carries evidence of that old system: chemical composition, moon orbits, internal structure, scars from ancient impacts, frozen gases from a vanished climate, deep minerals formed under conditions that no longer exist. A rogue planet may be a memory of a solar system we will never see. Part 24. The planet that never had a home. Now imagine another. It did not form around a star. It formed in a collapsing fragment of a molecular cloud. The cloud was cold, turbulent, threaded with magnetic fields. Stars formed nearby. Brown dwarfs formed. Disks formed. Jets emerged from young objects. Radiation carved cavities in gas. Inside one small collapsing pocket, not enough mass gathered to make a star. No fusion began. No bright sun formed. Only a planetary mass object condensed from the cloud. It was born alone. Warm at first, glowing faintly in infrared, surrounded perhaps by a small disk of dust and gas. Maybe moons formed there. Maybe a tiny system began around an object too small to be a star. It was never exiled. It was never thrown away. It simply began in darkness. Such an object challenges our language. Is it a planet, a sub-brown dwarf, a planetary mass object, a failed star below the usual brown dwarf boundary? The object itself does not answer. It exists. Rogue planets teach us that planetary systems are not always permanent. They teach us that formation is dynamic. They teach us that planets can be lost. They teach us that some planetary mass objects may form without stars. They teach us that the galaxy contains more than the luminous objects we see. They teach us humility about categories. They teach us that habitability may not be limited to sunlit surfaces. They teach us that darkness is not emptiness. Most of all, they teach us that the universe is full of hidden structure. For most of human history, planets meant wandering lights in our sky. Mercury, Venus, Mars, Jupiter, and Saturn were visible to the naked eye. Later, telescopes revealed Uranus and Neptune. Then exoplanets revealed that planets orbit other stars. Now, rogue planets suggest that planets may also exist in vast numbers between stars. The meaning of planet has expanded again and again. A planet is not only a companion of a star. A planet can be a wanderer. In the future, our view of rogue planets will become clearer. Roman may find many through microlensing. Euclid may continue revealing low-mass objects in star-forming regions. JWST and future infrared telescopes may study young planetary mass objects in greater detail. Ground-based observatories may identify more candidates. Surveys may map the abundance of free-floating worlds across different environments. With enough data, scientists may separate populations. Ejected planets, formed alone objects, wide-orbit planets mistaken for rogues, brown dwarfs near the planetary boundary, Earth mass rogues, Jupiter mass rogues, young, warm rogues, old, cold rogues. The hidden galaxy will gain shape. But even as we learn more, much will remain beyond reach. Most rogue planets will never be visited, many will never be individually named. Some will reveal themselves only once through a brief microlensing flash. Others will remain completely unseen. The galaxy does not owe us visibility. It holds more worlds than we can easily know. Of all rogue planet ideas, the most dreamlike is the starless ocean. A planet drifting alone. A frozen surface, a thick shell of ice. No sunlight, no weather above, no continents under a blue sky. But below the ice, perhaps water. A dark ocean warmed by the planet's interior. Minerals rising from vents. Chemical gradients, slow currents. Maybe simple life, maybe nothing. The idea is scientifically uncertain, but emotionally powerful. It suggests that habitability could hide in places we would never expect. It suggests that the universe may have secret environments, shielded from sight, independent of stars. It suggests that a world can be frozen outside and active within. A rogue planet's surface may be a locked door. The question is, what lies beneath? A rogue planet may not shine in visible light, but it may still produce a kind of light. Infrared heat, lightning, aurora, volcanic glow, chemical luminescence, the faint reflection of distant stars, the light from a nearby passing star, once in millions of years. In the far darkness, even small light matters. A lightning flash inside a hydrogen storm, a red glow from a volcanic crack in ice, a pale aurora over a magnetic pole. The universe is not divided simply into light and dark. There are degrees of darkness. Rogue planets live in the quietest degrees. Look at the Milky Way on a dark night. To the eye, it is a river of starlight. To a telescope, it becomes stars, clusters, nebulae, dust lanes, and distant structure. But even that is not the whole galaxy. There are black holes we cannot see directly, neutron stars too dim to notice, brown dwarfs cooling in silence, comets in distant clouds, asteroids, dust, gas, dark matter, and perhaps trillions of rogue planets. A galaxy is not only what shines, it is also what moves unseen. Rogue planets are part of that unseen galaxy. They remind us that the night between stars is not empty. It may be crowded with worlds. Somewhere, right now, a planet is crossing the dark. It may be large and gaseous, with storms moving beneath frozen cloud decks. It may be rocky, with mountains buried under frost. It may have moons. It may have rings. It may have an ocean sealed beneath ice. It may be young and warm, glowing softly in infrared. It may be ancient and cold, almost invisible. It may have been thrown away from a young solar system. It may have formed alone in a fragment of cloud. It may one day pass near another star. Or it may wander for the rest of cosmic time. Rogue planets are not mistakes. They are part of the universe's quiet abundance. They are worlds without sunrise, planets without years, islands without suns. But they are still worlds. They carry gravity, they carry history. They carry chemistry, they carry the possibility of hidden oceans, hidden heat, hidden stories. And as we drift towards sleep, they drift through the galaxy, silent, cold, patient, moving through the spaces between stars, the loneliest planets in the universe, and perhaps among the most mysterious.